you. I'm Chris Paolini. I'm from San Diego State. And today I'm going to talk to you about something a little different, how to actually use the PRP cluster for parallel distributed MPI computation. And we're going to look at a particular science driver where I'm going to show you a code I've been developing over about 4 years that simulates CO2 gas injection into the subsurface and also wastewater injection. So the topics we'll be talking about today are how to configure and test an environment for using OpenMPI on the Kubernetes network. Then I'm going to talk to you about benchmarking PRP with a tool called Linpack. And then I'll show you a science driver that I'm working on. I'm going to show you some simulations where we inject captured CO2 gas and then follow up that injection with wastewater to show you some enhanced mineralization. So to get started, of course, Dimo's already showed you this. You log on to Nautilus Optipeter Net and you go to the git config page. You authenticate using CI login and you download a client config bundle. And then you take that config file and you move it to your home kube directory. And you can get that using the git config menu option. So you put that in your .kube directory in your home directory on your station. Once you download that, you can check that the configuration is available to you from your station. So you can use kube control, kube control with your namespace, SDSU for example, cluster info. It'll tell you if the cluster is up and running. Then what you can do is you create your deployment using a YAML file. I'll show you that in a second. And then once the deployment is created, you want to verify that all the pods are up and running by looking at the running state. So you get a list of all of your pods. We have 8 pods here. They're all running. And you can see where the pods are actually located physically. So if you look at this, you can see that for this particular deployment, our pods are located at various spots in California and also in Wyoming and even Korea, on the Korean. So it'll be interesting to see how a distributed computational process performs when you're using all these nodes in a coordinated way. So the YAML configuration, now a lot of computational problems discretize a large domain into a fine grid resolution. And to represent these grids on multiple nodes requires a lot of memory. So in your YAML configuration, you can specify how much memory you need. For example, if you need 48 gigabytes, you can specify that using the request statement. And this is how much you desire. And you can also have a hard limit if you don't want to exceed 48 gigabytes. So that's where you can specify that. The other thing is your code that you work on, you're going to have to compile it on one of the pods to run it in that architecture. So you want to have a persistent storage, like I'm using NFS here. And this is where you specify your persistent storage. It'll tell you where you want to. External to the container, yeah. To the cluster, right. So you can mount set up NFS file system. You can mount that in say /NFS in all of the pods when the deployment is created. And that's where you can put your clone of your Git repository, and that's where you can build your code for the pod architecture. Okay, so I'll make all these scripts that I've written available to you in a Git repo, but the first thing you have to do is you have to initialize the cluster so that you can launch an MPI job using MPI run. So I created this shell script, just a simple bash script called init cluster, and we can look at it here. So what this does is it does really 3 things. The first thing it does is it'll iterate over all the pods that are created, and it'll generate a string of 3 tuples. consisting of an IP address, the host name of the pod, and the number of cores available to the pod. Okay, so we need this information to build the host file on all the pods and to build what's an shost equib file so that we can create passwordless key-based authentication between MPI processes. And also we need to create what's called an Mpi Host File that lists all the cores available on each pod. So we just iterate over all the pods and construct that string. Then the next thing we do is we iterate again over all the pods. And this is going to run on each pod another script I wrote called setup sh, and it's going to take that 3-tuple array as an argument, and it's going to install packages we need on every pod and configure the client and server SSH and SSHD config files for key-based passwordless authentication. It'll also, at the very end, start up the secure shell server on each of the pods. And you have to do that first before you do the third thing right here, which is, again, iterate over all the pods. This time it's going to call another script called update keys, and that's going to gather all the keys for the known host file so that you can do passwordless authentication between the pods. So if we take a look at the setup script, and there's a better way of doing this, which I'll show you after I show you the script. But this is the script that gets invoked on every pod through the init cluster script. And the first thing it does is it installs the packages you need. So obviously you're going to need the OpenMPI packages. You're going to need any compilers or any development libraries you need to build your numerical code. So that's what these lines do. Then the next thing I do is I save my default etc host file because I need to regenerate it based on the host names of all the other pods in the cluster. When the pod starts up, it doesn't know about any other pods that are part of your deployment. So all the pods have to know about each other. Now, it's a best practice or a better practice not to run your numerical code as the privileged root user. So if you want to not run as root, you can create a fictitious user just for the purpose of running your simulation. So that's how I do that there. I first check if such an account exists. This is some fictitious name, and then you can do group and user add to generate that user account. Then the next thing we do is we have to configure on each pod the client and server SSD configuration files to allow passwordless key-based authentication. So that's what the rest of these code sections do. So the first thing we do is we have to construct the shost equib file. This is going to enable passwordless access. We're going to enable authentication for the root user. So we're going to construct this /root/rhost file. That's what we do here. We're going to configure SSD to accept the host name provided in the packet itself and not have the pod use a DNS resolver, okay, because there's no DNS resolution really within the pod. So you have to enable this host-based use name from packets only configuration. So we include that in there. Then this next section of code will allow authentication from the root user, okay, if we want to run as root, which we're going to do. And then finally, we rebuild the host file. We made a backup at the very beginning, and now we can rebuild this file because we know from the argument lists that get passed in, we know the host names of all the other pods in our cluster. And then what we do is we construct this Mpi host file. So this is a file of all the host names of all the pods in our cluster, but it also has these slots lines, slots and max slots. And that tells you how many cores are available on each pod in your cluster. Finally, we start the SSH server. We'll stop it if it's already running and then restart it so that it runs under the new configuration that we just created in this setup script. The third thing we did in the init cluster script was to call the update keys script. So all the SSH servers have to be running on all the pods in order for the update keys script to work. And all this does is it iterates over all the pods, calls SSH key scan, and then it generates on each pod this SSH known host file. And after you've done these steps, you can use MPI. Now, one of the things I did in the init cluster script, or the setup script, was I installed packages. And of course, you don't need to do that. What you can do, and this is, Dima showed me how to do this, is you can create a Docker file. And here's a Docker file, very simple Docker file. And in that, you can specify in the run directive the packages you want to have installed. And then you can pull that Docker image and create an image. And then once the image is available, you can specify that as your image in your YAML file. So then, okay, so once that's done, you can call Docker images again. You can see that new custom image that got created with your packages already installed. And then once you create the deployment, you won't have to wait so long for apt-get to install all of your packages. It's just going to do the SSH client and server configurations and gather all the keys. So the benefit of using a custom image is your deployment time is reduced. Okay, so if you log on, after you run the init script, if you log on to any one of the pods, you can look at the created Mpi host file, and you can see for any particular pod that got created in your cluster, you can see how many cores were found to be available. So there's different, different architectures on the PRP network. You can see some machines have a lot of cores, some, not so many. Maybe the common denominator here was 8. This has 96 cores available. So we'll use 8 for our simulation since that's the common number available on all the pods. Okay, so the first thing, one of the common tests you want to perform when you set up MPI is you want to perform the ring test. So this is an example run script on how you invoke an MPI job on the PRP network. So in this script, I just define my namespace. I define my cluster base name. And then I just have in a switch statement here the instruction to run. So how it works is you call kube control, but your executable is the MPI run tool. And here we're going to run these as root. It's not the best practice, but it's efficient. And you specify the host file that got created in the initialization script. You specify this MCA parameter, which is going to use TCP for communication, because as I was talking with Dima, InfiniBand fabric isn't available yet or visible in the pod jail, so to speak. So you have to use TCP for communication. So you specify that. You specify the number of processes you want per pod and the total number of processes invoked. So here we're going to invoke 8 processes, 1 per node. So one pod is going to run 1 process. You're going to bind each of those processes to an available core, and then you specify the executable that you want to run. So for example, I can run this for you now. Okay, so it's running the ring test. It tells you our pods, and it's completed. So, excellent. Okay, so all the ring test does is it verifies connectivity. It'll basically tell you if your MPI setup is working. And all this test does is it passes a float around the ring of processes some number of times. I reduced it in that test so it would run quickly, but for example, it'll pass a variable around 2 to the 10 times, and each process will increment it by 1. And then it'll output the product of the number of times around times the number of processes in your cluster. So you get 8192 here, that's correct. So to just performing the ring test will just verify that your MPI configuration is working and all pods can communicate with one another. Yes, sir. So the IB fabric can't be seen within each pod. I was just talking to Diem about this. So it is doing IB over Ethernet. It's IB over Ethernet, right? But I was actually talking with Diem about this quite a while ago. So I think there's a way that we can mount the IB verbs directory within each pod and somehow get it to work. So we're going to work on that. Right now, though, it's not available. All right, so one of the things you want to do, or one of the tests you can use to evaluate the performance of a cluster is to use the Linpack Benchmark. And a lot of numerical codes solve a set of partial differential equations or ordinary differential equations, and that typically results in the repeated solving of a set of linearized equations. So a lot of codes will linearize nonlinear equations and then solve them if it's an implicit method. And if you are solving like systems where your coefficient matrix doesn't change, just your right-hand side is changing, one of the fundamental matrix factorization methods is called the Lu factorization, where you decompose a coefficient matrix into a lower triangular and an upper triangular matrix, and then you can use those factors to repeatedly solve a right-hand side. So performing Linpack or evaluating your cluster using Linpack gives you a good idea, rough idea of how well your cluster will perform. So the idea of this benchmark is you're going to repeatedly do LU decomposition with partial pivoting. You're going to save your pivoting operations in a permutation matrix P. And what you want to do is you want to identify R max, that is the best floating point rate for a particular system dimension n. So we want to find R max for a particular n, where we also vary some other attributes like the grid assignment, which I'll show you. Okay, so the idea of this benchmark is you have a system, you want to solve AX equal B for a given n. You're going to do an LU factorization of A using partial pivoting. So once you construct LU, you can quickly solve, because you have Ly equal PB, you solve for Y using forward substitution. And then you can, once you have Y, you can solve for X by solving Ux equal Y. So this is a complexity of 2/3 n cubed flops. And what matters in the performance is how you decompose your matrix into blocks of a given dimension NB. And what also matters is how you partition those blocks to your MPI processes over a particular P by Q grid space. So these are some properties we're going to vary and see what kind of performance we can get on the PRP cluster over the PRP network. So if you're not familiar with this, of course, you have a system, coefficient matrix A, a very large matrix that you need to factor. You can decompose that very large matrix into smaller submatrices, blocks of size NB by NB, and then if you partition those to MPI processes, the partitioning will yield the so-called block equations. So the block size is the size of the decomposed blocks of dimension NB by NB. And what we want to do is we want to see how does changing the block size yield different performance metrics in terms of a gigaflop count on the PRP8 cluster. Now, one of the things we can have control over is how those blocks of dimension NB are passed and assigned to each process in your MPI cluster. So this is done cyclically, and this will affect how this will affect your memory access pattern as you're doing the overall factorization. So if you choose a process grid of P by Q, say for example 2 rows by 3 columns, you can see over here we have 2 rows and 3 columns. So each one of these colors represents an MPI process running on one of the PRP nodes. So how you vary this, how you choose your process grid controls how you assign these subblocks, which are then factored individually by each node. Okay, so how do you launch this benchmark on the PRP? So again, this is part of the run script I've developed, and I'll make these scripts available to you in a GitHub repository. But the idea here is the actual benchmark is called XHPL. So you compile that on one of the pods, and you make it available in your mounted NFS directory. But this is how you invoke it. So it's very similar to invoking the ring test. This time we're going to do 64 processes, okay? And we're going to have 8 processes per node. So we have 8 pods, 8 times 8, 64. And then we're going to invoke the benchmark, and we're going to store our results in a file called XHPL out that we can then plot, extract information, and plot using MATLAB, for example. Okay, so these are the results of benchmarking on the PRP allocation that I showed you, and I used 4 different grid configurations, and you just happen to see that on a PRP network, if the larger block size gave us better results. So we got about the best I got was a little over 7 gigaflops. And this was with the larger block size of 256. And I had the best results on a 2 by 32 grid. So that particular distribution performed the best. Now another parameter that you can vary is called it has to do with the method or the algorithm you use to factor each panel. And typically Kraut performs best, Kraut's algorithm. But we can see if we can get better performance if we vary the panel factorization algorithm, which I'll do next. But one thing I want to show you is, so as we launch the benchmark, if you then in a separate window go to Grafana Nautilus Optiputer Net, you can see the load induced by performing the benchmark on the cluster. So you can see the load shoots up quite a bit, and you can see when the benchmark ends. Okay, so the way that you configure the benchmark is you modify this file called hpl.dat, and here's where the relevant lines are. These are where you specify values of n. So I chose values from 2 to the 7 to 2 to the 15, and then here you specify your block sizes. You want to choose n such that NB is aligned, okay, to get the best performance. And Jack Dongara, who developed this benchmark, recommends block sizes between 32 and 256. They typically yield the best performance. The other thing is you specify your different grid configurations. So you want to choose Q greater than P, where the product PQ equals the number of processes you invoke. So we invoke 64 processes in our run script. So these are values where PQ equals 64, where I have Q greater or equal to P. Okay. Now another thing you can play with, as I mentioned, was the panel factorization algorithm. There's 3 different ones you can choose. One's called left-looking, one's called right-looking, and the other is Kraut's algorithm, developed by mathematician Prescott Kraut. So you can visualize. Right-looking is the easiest to visualize. So just quickly, if you want to factorize a matrix like this, A, and you've already factored your first column and first row, you will be left with this green submatrix to factor. And you can see that this green submatrix is totally independent of these blocks that you've already previously factored. So you can recursively decompose and factor a matrix by factoring each row and column, and then recursing to develop this lower to the right submatrix. Of course, once you do that, if you recurse and then you have this smaller submatrix, you can consider that independent of the larger matrix. Once you factor the first column of this smaller submatrix, you already have L11, L21, and L11. Then you can quickly solve for A12. Once you do that, you can solve for an approximation of A22 and then recurse again. So this is called right-looking because you're sort of going to the right through recursion, factoring each submatrix that you form. So if you look at the memory access pattern from these three different methods, this is sort of the template that you have. Here's the right-looking that we just saw. Kraut looks like this, and then there's another one called left-looking. So we can experiment on the PRP network. We can see, does it make a difference which panel algorithm we choose? Well, I did that test with left, right, and Kraut. I only found that Kraut performs slightly better. So I got 7.056 gigaflops, which was better than left or right, but didn't make that much of a difference. Okay, so we only got about 7 gigaflops on the PRP network, and that's not such a good score. So let's try and see how Comet improves things. So it turns out we can have access to Comet through the same Kubernetes mechanism. So we just have to develop another YAML configuration, this Comet YAML. And here I created a deployment on Comet, and I just have it under a different namespace, just -Comet. You can see that these pods are now running on Comet. So we can do the same benchmarking and see how does Comet improve things. So I ran the same benchmark on Comet, and here you can see that as n increases, the block size makes much more of a difference in your overall Rmax value. You can see that also another difference between PRP network and Comet is on the PRP network we saw that a larger block size gave best results, but on Comet it was exactly the opposite. I got the best results with the smallest block size of 32. On the same PQ grid assignment, though, this is the 2x32, but you can see the smaller block size makes much of a difference, and block size begins to make more of a difference as n increases, as your system size increases. The other thing is to look at the score. So it's order magnitude 10 times the performance that you get on the PRP cluster. So I got 47 gigaflops on Comet. 64 processes, right? 64 processes, yeah. Exactly the same benchmark. It's very low, and this is what we're seeing as the overhead incurred by the Kubernetes infrastructure on the overall benchmark. So it's no, there's also no InfiniBand, so it's over TCP. One order of magnitude higher, yeah. Yeah, of course. You can get, well, I'm sure you can get a teraflop score. You could get like 30 teraflops on Comet. But that's not really, this is something new, right? So we're using Kubernetes in kind of a new way. So we're not expecting to get traditional performance. This is just something interesting. Yeah. Yes, sir. Right. Remember the original slide? They were distributed over large parts of California and even in Korea. So there's going to be quite a bit of latency in data exchange, and that's going to have an effect on performance, of course. But we can do a comparison of the pros and cons of running on regular PRP and Comet. So for example, in the PRP network, you got slower numerical performance. However, there are some advantages. One is there's no restriction on wall time. So my pods have been running for many weeks on the PRP network. There's no real formal approval. I didn't have to write a proposal to get an allocation. And running on the PRP network didn't require as much administrator intervention. I was able to operate mostly by myself, getting these things done. However, on Comet, you get superior performance, but there are some restrictions. One is, on Comet, you can't have a job run for more than 2 days. And a lot of my simulations can run for actually months at a time. So if you're doing simulations that are simulating in geologic time, where you have many time scales or different overlapping grids or grids of different refinements, you can have 2 days is too short of a time. So also you need to write a proposal and have it approved by SDSC to get an allocation. And then the other disadvantage is if your pods are left running but you're not actually running jobs, it still counts towards your unit allocation. So you have to shut down when you're not using them. Whereas I can leave my pods running in PRP indefinitely, All right. So that's benchmarking. So now I want to talk about how I'm using the PRP network for an actual research project. And we're looking at mineralization or enhanced mineralization during carbon sequestration by using a concept called excess alkalinity. And I'll talk to you a little bit about that. So one of the projects I'm involved in are exploring synergies among 4 different processes. One is wastewater management. One is producing biofuel using algae. One is through enhanced oil recovery, and the other is carbon sequestration. So if you're not familiar with enhanced oil recovery, the idea, 30 to 60% of oil that's extracted is done using this process. And what it involves is you inject CO2 gas at a very high pressure into a reservoir. And that CO2 reduces the surface tension of oil, and it dislodges oil from trapped pore space in rock. And that CO2 gas pushes this effluent downstream, dislodges oil, and pushes it towards a well downstream called the production well. And out of the production well comes the oil that was dislodged, but what also comes out is a lot of brine water. So all the water that's pushed towards the downstream well, that all comes out too. And for every 1 barrel of oil that gets produced, it generates 10 barrels of water. And this water is a major expense of an oil and gas company. The management of water is about 55% of the operating expenses of oil and gas company. So you have to dispose of this water. This water has heavy metals in it. It has toxic organics in it. It's very salty. You can't use it for any agricultural use. You certainly can't drink it. It has radioactive isotopes in it. It has isotopes of radium. So it has to be disposed of properly, and that costs a lot of money. So typically that water is reinjected back into a wastewater injection well. Now, anything we can do to reduce the cost of managing that water is going to reduce the cost of a barrel of oil. So one of the ideas we're working on is how can we use that produced water for something useful? Okay, so the idea is you need a source of CO2 for the enhanced oil recovery. So that can come from, say, a coal-fired power plant. If you can capture the CO2 and then use it for injection into this EOR well. Well, once the water comes out, what we can do is we can take that water and we can store it in very large pools, vats. And we can grow algae in that water. There's some species of algae that thrive in very salty environments. So we can divert that water, grow algae here, and we can cultivate that algae and extract from their lipids and make diesel fuel. So we can create diesel fuel from their fats. We can also take wastewater from sewage, and which is high in nitrogen and phosphorus that algae need, and we can divert that into the pool, so that's something useful. Now, what's very cool about this process is through photosynthesis, the top layers of the water will increase in alkalinity, so the pH will increase. And we can siphon, if we can siphon that highly alkaline water off and store it, and then after we inject CO2 into the subsurface for sequestration, we can take that highly alkaline water and inject that and see if that can increase the rate of mineralization. And I want to show that through numerical simulation, and we want to run that simulation on the PRP network. So we're going to validate this process through simulation on the PRP network. So if you're not familiar with this, the science behind this, carbon sequestration is probably the best way to deal with climate change. And that is we continue to use fossil fuels, but we trap the CO2, and instead of allowing that CO2 to go into the atmosphere, we inject it deep in the earth, into the subsurface. Now, there's risk involved in that when you inject CO2 gas into the subsurface, you want to make absolutely sure that CO2 doesn't come back out into the atmosphere. That would defeat the purpose, right? So anything we can do to reduce the risk of that happening is ideal. And the best way to reduce that risk is to take the carbon that's in CO2 and transform it into a solid phase mineral. So the carbon in CO2 gets moved into the carbon in, say, calcite or magnesite or dolomite. So we want to neutralize the carbonic acid that gets generated when you inject CO2 into water, and we want to as quickly as possible precipitate one of these carbonate minerals. Okay, now ordinarily this process of precipitation takes 100 to 1,000 years, and that's too long of a time, and that's too risky. That's too risky for the gas could migrate back out to the atmosphere. So what can we do to speed up this process? Okay, so if you look at what happens as you inject CO2 into the subsurface, there's really 4 different ways that CO2 is stored. The ideal way, again, is mineral trapping. And if you look at this time scale, that occurs, say, 100 to 10,000 years where this occurs. So what we want to do is we want to find a way where we can stimulate a reservoir after we inject CO2 to increase the rate of this mineralization. Now, it's a problem because injecting CO2 gas into water and precipitating calcite are actually competing processes. What happens is if you inject carbon dioxide into water, you'll form carbonic acid. But if the concentration of carbonic acid increases, you'll actually dissolve the mineral that you want to preserve. So if you increase the concentration of CO2 gas, these reactions shift to the right, and the calcite that you want to preserve dissolves. If you precipitate calcite, you actually produce CO2 gas. Actually, as corals form, CO2 gas is produced. So these are competing processes. The problem is, how do you store CO2 gas and precipitate calcite at the same time? What can you do? Well, what we could do is first we have to look at what's called alkalinity. So alkalinity is just a measure of a solution's ability to neutralize acids. So the alkalinity will increase as you dissolve a carbonate mineral, right? Because if you dissolve calcite, you produce carbonates. That increases the concentration of carbonates, which increases your alkalinity. However, if you precipitate and form a carbonate mineral, it'll actually decrease alkalinity. So the idea would be to store CO2 and precipitate calcite, you have to somehow increase alkalinity. So you have to have some kind of excess alkalinity. And the way we can do this is from that algae pond that I talked about. So if we introduce an external source of alkalinity as hydroxide ions, then all of the carbons in a bicarbonate can go to a carbonate mineral, and the rest of the acid is neutralized to form water. So we want to simulate and model this kind of science by running a simulation on the PRP cluster, and we want to see if this by supplying this excess alkalinity actually precipitates carbonate minerals faster. Now here's a picture of an operation in China. So they have these large algae pools, and they're supplying CO2 for photosynthesis by collecting CO2 gas from their coal-fired power plants. So these are the reactions involved in photosynthesis. The carbonic acid is transformed into formaldehyde, and these are other reactions that produce formaldehyde, but you can see two of these reactions produce the needed hydroxide ions that we need as a source of excess alkalinity. So we want to extract that highly alkaline water and inject it after we inject CO2 to see if we can precipitate carbonate minerals faster. Now another thing we need, in addition to the alkalinity, is we need a source of alkaline earth metals, calcium and magnesium, to bind to those carbonates. So in addition to excess alkalinity, we also need a source of excess hardness. And what's great about produced water that comes out from an EOR operation is the concentration of calcium and magnesium is much, much greater than even salt water. So the produced water is a great source of excess hardness. Okay, so with excess hardness and excess alkalinity, we want to simulate this using code and run it on the PRP cluster. So for my experiments, I have 4 different kinds of grid resolution where I vary the resolution along the Z-plane. And this is modeling what's called the Frio Formation, which is in Houston, Texas. This is a system that has 3 sandstones separated by 2 shale layers. So we have these grids that vary in the Z-axis. And hopefully I can show you a simulation. So this is the results of running on the PRP network. And this is just simulation showing injection of CO2 into that grid. So these are results that were obtained by running on the PRP cluster. You can see the concentration of carbonic acid as you inject. I'm injecting here at the origin. Okay. So here's my mineralogic composition of sandstone and shale. So I have a sandstone and then these two shale layers. Here I'm injecting a CO2-rich injectant. I have a 10 millimolar solution of CO2. Okay. So the code, I'm not going to go through all the models that it solves, but the important ones are it solves the velocity and pressure relationship in a porous media. So it solves Darcy's law and with the continuity equation constraint. We have a poroelastic model which simulates rock fracturing. So as you inject CO2 gas at high pressure, you'll have fractures in the rock, which affects the permeability and the fluid flow within the reservoir. And the most important system is this elemental mass transport model. This governs the transport of all the solutes in the water, like carbonic acid, bicarbonate, carbonate. Now, here's a plot using ParaView of a result obtained on the PRP cluster. This shows a plot of what's called saturation. And this is just a measure of where it's thermodynamically feasible for precipitation to occur. It doesn't tell you that precipitation will occur or how fast it will occur. It just tells you if it's even possible to occur. For precipitation to occur, your saturation value omega has to be greater than 1. So if we just plot that, we can see this is a region where we could expect to see precipitation. And the reason why it's higher over here is because I'm injecting normal to the YZ plane. So I'm injecting along the x-axis. I'm injecting CO2 along the x-axis. So there's an increased saturation in this region. Okay, so these are results on the PRP. Okay, so this is just, I believe this will work. Not animating. Well, I can skip ahead. So this is, I'll skip all the way to the end here. Okay. Oh yeah, it's animating. It's animating slowly. Okay, so this is a result running on the PRP network. So this is a simulation where I inject CO2 gas at a mass rate of 1 kilogram a second, and then I stop for 1 day. So I inject CO2 gas for 1 day at a mass rate of 1 kilogram a second. Then I stop for a day, I do nothing. And then I inject that highly alkaline wastewater at 1 kilogram a second for 1 day. And then I let the reservoir equilibrate for 5 years. And you can see in that region where saturation was greater than 1, we're seeing the volume fraction of calcite increase. So we're seeing just in 5 years precipitation of calcite occurring at that region where it would have normally taken 100 years to form calcite. So this is with one solution where it's highly alkaline, so it's pH of 12, but it has low hardness. So the next test is one where we have the high hardness. Okay. So this is 10 to the 5 now, so it's greater scale. So as we increase the hardness, we increase the availability of alkaline earth metals, and we see that we can precipitate much faster. So a lot of that calcium and a lot of the calcium in the produced water is going into forming calcite. Okay, so running. Oh, this last test I forgot to tell you, this was run on Comet. So I ran this case on Comet. So this is a script to actually run this simulation. So it's just like the ring test I showed you. So we define our namespace, we define our cluster base name, and you can see here I'm running kube control. So here again, we specify the host file. This is four processes, 1 process per node. The reason I did that is because on Comet I only was able to get 7 pods, but I need a power of 2 for my allocation, so I chose the closest power of 2 less than 7, which is 4. So I have 4 processes, 1 per node, and I run my simulation. And when it starts up, you can see the process allocation map. Okay, so that's how to do it. All right, so in conclusion, we were able to show using the PRP network that it is feasible to induce early carbonate mineral formation through injection of highly alkaline water following CO2 injection. And so now we're working on these things. Again, how does alkaline supernatant refers to the top layers of water of the algae pond. How does that increase the mineralization rate of calcite and dolomite following injection? So these are the research topics that we're pursuing now. Any questions? Yes, sir. So in my YAML file, a 32 gig. So I had a 32. Oh, like if you run these and you're running top, you'll see these processes are like 8 to 10 gig. 8 to 10 gigabyte of allocated memory. Yeah, like if you're running a top. Yeah. So actually, let me qualify that, because that depends on the grid I'm using. So as I increase my grid resolution, that memory increases. Yeah. Any other questions? Yes, sir. Yes, sir.
I've only run on the open science grid before, but could you compare with what sorts of features on the PRP were better or easier or not available on the open science grid?
So I have an OSG allocation. I haven't used it that much. I can't really comment on what's better or worse. For this project, though, it's all about the PRP. So I focused entirely on the PRP. So I don't know what OSG provides that's better. I'm sure this will work. I can do a benchmark on the OSG and see and do a comparison. They don't require a proposal, right? The proposal is not a big deal, but it's a little bit. The real problem with Comet is the 2-day wall time restriction. That's a killer for me. Okay.
So, so Comet is one of the supercomputers. Blue Waters is another one. Stampede, et cetera, TAC, Extreme at Stanford. Those are all, if you add them all up, and if anyone wants to correct me, but the last I looked, OSG is delivering more than that every month. And so you shouldn't run into the wall clock restrictions.
The only thing I would say to that is my impression of OSG is good for short running jobs because a lot of the cycles are cycle scavenged, and so jobs can get interrupted. And so unless you've basically you have to do checkpoint restarts in the same way you would have to on Comet. And I think it's actually less predictable on OSG than it would be on Comet.
Yeah, that's a good point. And I was also going to comment that, here your application is MPI, and you're able to take advantage of the tight networking between the PRP end nodes, and sort of you're doing wide area MPI, which is pretty unusual to begin with.
Right.
But you're on a fabric which is well connected. In Open Science Grid, of course, we have diversity of different kinds of network connections between hosts, and so you might run into an issue there as well.
Is InfiniBand fabric available on OSG nodes?
Well, OSG is really meta layering over many different facilities, and some of those do have, of course, InfiniBand locally. But of course, there's nothing like that over the wide area between nodes, between sites.
Other observations or questions for Chris?
Yes.
Seems like a lot of work to get from the setup that you had in getting to the point where you're running the MPI applications in a Kubernetes cluster. There's definitely a lot of work there in order to get there. So is there any benefit for Kubernetes in running your MPI applications, or should MPI applications just be part of a different kind of infrastructure?
Well, you say a lot of work. Once the scripts are working, then I can at will just use my run script and just launch jobs without any trouble. So launching jobs on the PRP Kubernetes infrastructure is pretty easy. Now, in terms of are there advantages? Well, one of the things I want to explore is I haven't fully containerized my application yet. So I want to look at how can I containerize my code and then launch a bunch of jobs with different configurations and let them run and see how the flexibility that Kubernetes gives you makes that attractive to use Kubernetes for these scientific workflows. Now, the performance is limited, but I would say the ability to just launch jobs is so simple that Kubernetes makes it just very easy to launch jobs. So I would say the opposite of what you suppose, that it's very little work I had to do to set this up, and now I can just willy-nilly launch jobs. And if I fully containerize this, I think I can just quickly deploy many runs with different configurations and let them run and then collect results. Now, another thing I want to work on next, I didn't talk too much about next steps, but one thing we want to do is we use peer review. I didn't show peer review. I'm not sure. Yeah, so. So one thing you can do in peer review is you can set up a data server in peer review and then a rendering server separately in peer review. And with your peer review client, you can connect to the rendering server. And that rendering server can be distributed using MPI. So we can have in Kubernetes pods running parts of a decomposed rendering service. And then what I like to do is use the peer review client to connect to the rendering services in Kubernetes to do distributed rendering, where it's pulling the visualization data using distributed data services, where the data services are gathering information from a very large output file. So I didn't mention it, but we have a 2.2 petabyte BGFS storage system where I'm generating very large data sets of these simulations. So 100 terabyte files. Now, a 100 terabyte file is too inconvenient to download to your workstation to visualize. So to answer your question about how Kubernetes could be very useful, it could be useful in that if we could set up a system where we have these distributed peer review data and rendering services and be able to visualize these very large data sets without having to download those files locally, I think that would be very advantageous. And that's something I'd like to pursue next. Yeah. Any other questions? Did I answer your question a little bit? Yeah. Yeah.
I just did a quick calculation, right? Since each of your MPI rank use about 8 gigabytes memory, right? Nowadays, I think a typical node of the Kubernetes cluster actually has 250 gig of memory. So presumably, all your simulation, right, can fit into a single physical node. And if you simply take a physical node, you run it, I guarantee it's two order of magnitude faster than
Sure.
running through Kubernetes.
I mean, one of the motivations of not doing that, just having one process per node, was just to sort of utilize the physical distributed nature of the PRP network.
Yeah. This is
just for
no.
the
I
sake of
really,
doing
I
it.
really
Yeah.
applaud. This is
Yeah.
great. I learned a lot from that process. I'm just thinking about the best way of utilize the resources. Yeah.
Thank you.